Good evening, everyone. Welcome to this live session, which is relevant to week 10 in the NPTEL course in fluid mechanics. So, I'm sharing my screen. So, I hope my screen is visible to all. So, this particular live session, which is basically deals with the contents related to the week 10 on the course on fluid mechanics by Professor Subhashis Datta. So, the main content of this week 10 is the derivation of Navier-Stokes equations and some situations, some simple applications of Navier-Stokes equations or some fluid flow situations for which the exact analytical solution of some simplified flow situations where the exact analytical solution of Navier-Stokes equation is possible. So, if you have gone through the lectures, you must have understood that uh, this that how to derive Navier-Stokes equation and then how to use this Navier-Stokes equation for solving simple flow problems like flow between two parallel plates or flow inside a pipe. Okay, so in today's session we'll be solving few problems which are related to the application of Navier-Stokes equation. The Navier-Stokes equation is nothing but the conservation of linear momentum in case of fluid flow. So this equation is very important, and Navier-Stokes equation, the exact analytical solution for the full form of the Navier-Stokes equation is a millennium problem. Means if somebody can solve that problem, there is a prize money of $1 million. As you can find the details, the page by Clay Mathematical Institute. You can find the details in the website of the Clay Mathematical Institute. Anyways, so let us start. So the first problem: water at a temperature of 60 degrees Celsius flows between two large flat plates. The lower plate moves to the left at a speed of 0.3 meter per second. The plate spacing is 3 mm and the flow is laminar. Determine the pressure gradient required to produce zero net flow at a cross section. And the value of the dynamic viscosity at 60 degrees Celsius is 4.7 into 10 to the power minus 4 Newton second per meter square, but it is for water. So what is the situation? The situation is there are two large flat plates. So this is the top flat plate, this is the bottom flat plate. Okay, and at a temperature of 60 degrees Celsius, water flows between these two plates. The lower plate, the bottom plate, it moves towards the left. Okay, the bottom plate is moving towards the left at a speed of 0.3 meter per second. Means the bottom plate is moving towards the left at a speed of 0.3 meter per second. The spacing or the distance or the gap between these two plates is 3 mm, and it is given in the question that the flow is laminar. Now what you need to find? You need to determine that what is the pressure gradient. Okay, what is the pressure gradient required for maintaining zero discharge or zero flow rate. Okay, pressure gradient required to produce zero net flow. Okay, zero net flow at a particular cross section. Okay, so this is what has been asked. So let us see. So as we can see that we can directly solve this problem by Navier-Stokes equation, but it does not. We don't have to deal with the entire or the general Navier-Stokes equation. So the procedure for solving this kind of problem is, if you want to learn conceptually, you start from the very basics. You write the entire or the general form of the Navier-Stokes equation. You see what are the assumptions that you need to apply. Okay, few assumptions are given in the question. For example, the flow is laminar. Okay, and based on the flow situation, you need to decide what are the valid assumptions for this problem. Then after the application of the appropriate assumptions, you derive the simplified form of the Navier-Stokes equation for this situation, and then you decide the appropriate boundary conditions, and then based on the boundary conditions and the suitable form of the Navier-Stokes equation, you solve the problem. Okay, so let us see what is the solution. Now the governing equation, that is the Navier-Stokes equation for this situation. Okay, now if you apply the suitable, so you can see that the problem can be considered as a two-dimensional problem. Okay, so the Cartesian coordinate system adopted for this problem are this. So towards right is the positive axis, and towards top is the, as you move from bottom to top, it is the positive y-axis. Okay, the distance between the two plate B as given in the question is 3 mm. Now as the bottom plate is moving towards the negative x-axis, so the velocity is denoted as minus u. Okay, and the value of u is, the magnitude is 0.3 meter per second. Now the appropriate form of the Navier-Stokes equation that we can use for this form, okay, is mu d2u dy square equal to dp by dx. Okay, so what is the appropriate form of the Navier-Stokes equation that you can use? The appropriate form of the Navier now is mu d2y dy square equal to dp dx. Now if you have gone through the lectures of week 10, you must have very easily understood how this particular form or this equation has been achieved. Okay, now what is the governing equation? Governing equation is mu d2u dy square equal to dp by dx. Okay, now from this we can as you have already gone through the lectures, okay, as you have already gone through the lectures, you must know by this time that for this kind of situation, okay, for this kind of situation, the pressure gradient dp by dx is a constant. Okay, it is a constant. So from this, what will be d2u by dy square? d2u by dy square is equal to 1 by mu dp dx. And if it is 1 by mu dp dx, what is the expression for u? The expression for u can be obtained from this particular equation simply by the double integration technique. That is the easiest technique for solving differential equation. Okay, so double integration. Now if you apply double integration, you will get u is equal to 1 by twice mu dp dx y square plus c1y plus c2, where c1 and c2 are constants of integration. So this is a very simple step, but in order to obtain a unique solution for this differential equation, or unique solution in terms of u, you need to have unique values of c1 and c2, because this particular equation is valid for any constant c1 and c2. Okay, but this flow situation, okay, is valid for only one pair of c1 and c2, one unique pair. So in order to determine that unique pair of c1 and c2, you need to have the boundary conditions. Now what are the boundary conditions? At y equal to 0. Now see, if you consider that the origin lies on the bottom plate, then at y equal to 0, u is equal to, see, the bottom plate is moving towards left. Okay, so u is equal to minus u. So this particular equation, if you put here these conditions, if you put in this equation, you will get c2 equal to minus of u, and the upper plate is stationary. So at y equal to b, okay, at a distance b, u is equal to 0, which gives the value of c1 as u by b minus of 1 by twice mu dp dx b. So simply substituting the values of c2 and c1 in this equation, we get u is equal to 1 by twice mu dp dx y square by plus u y by b minus 1. Now you can see that u varies with y, okay, and the variation is parabolic in nature because y square, okay, the y square term is there, so the variation is parabolic in nature. Now in order to obtain discharge from this u, q, that is discharge from this u, what is the form? Okay, how can you, so what is discharge? Okay, what is discharge? Discharge is q, okay, is area into velocity, right? Area into velocity. Now here, now this velocity in this expression is the average velocity, but in our case we don't know the average velocity, but at different values of y, at different spatial location, the variation of u with y is given to us. So what will be the average velocity? Average velocity, see, it should be u if you consider this is y, and if you consider a small stretch, okay, whose area is dA, then for this stretch, through this stretch, what will be the discharge? It will be dq. Okay, so dq will be u dA. Okay, now what is dA? If you consider what is dA, dA is basically, now if the width, now width, what does it means? Means the dimension that is perpendicular to the plane of this particular plane. Okay, the plane of this whiteboard, okay, or the Google board, the plane perpendicular to this Google board is the dimension perpendicular to this plane, okay, is the width. Okay, so say the width is w. Okay, say the width is w, so dq can be written as u w dy. Okay, now in this case the width is not given in the question, so in such a case what you can do, you can safely assume that the width is equal to 1. So if the width is equal to 1, then dq is equal to u dy, and if dq is equal to u dy, what will be total discharge? Total discharge will be integration u dy, but integration from where to where? Okay, integration from where to where? So from y equal to 0 to y equal to b. Okay, so from y equal to 0 to y equal to b. So this is the discharge. So that's what has been done here. Integration u dy 0 to b. You put the expression for y. Now this is a very simple integration. So once you do the integration and you apply the limit of integrations, you will be getting q is equal to minus of by 12 mu dp dx b cube minus of ub by 2. Now what you need to find? You need to find the value of dp by dx for which q is equal to 0. Now in this equation, if you put q equal to 0 and the value of mu as 4.7 into 10 to the power minus 4 Newton second per meter square, which is supplied to you in the question, the value of dp by dx is minus of 6 u mu by b square, and after substituting the appropriate numerical values, it comes out to be minus of 94 Newton per meter square per meter. Okay, so this is the first problem that we have seen, which is directly related to the application of Navier-Stokes equation. I hope this problem is clear. In case of any doubt, you can ask. Okay, so let us summarize this problem once more. So in the problem, what is asked from you? You need to determine the pressure gradient. Okay, in the problem you need to determine the pressure gradient dp by dx. Okay, the pressure gradient for which the value of q is equal to 0. Now the situation is, there are two parallel plates and the flow is taking place, flow of water between these two parallel plates at a temperature of 60 degrees Celsius. Why temperature is important? Because the viscosity of the fluid, we know that it varies with temperature. So at 60 degrees Celsius, it is given to you that the value of the coefficient of dynamic viscosity is 4.7 into 10 to the power minus 4 Newton second per meter square. Then the two plates are separated by a distance of 3 millimeter. The flow between the two plates is laminar, and the upper plate is fixed, or the top plate is fixed, and the bottom plate is moving towards the left at a speed of 0.3 meter per second. So after making suitable assumptions, the form of the Navier-Stokes equation in this simplified form that is suitable for this problem is mu d2u dy square equal to dp by dx, and after double integration, u is equal to 1 by twice mu dp dx y square plus c1 y plus c2. Now in order to determine the value of c1 and c2, that is the constants of integrations, we have applied the boundary condition. The boundary condition is at y equal to 0, small u is equal to minus of u, which is 0.3 meter per second, and at y equal to b, small u equal to 0, because the upper plate is stationary or fixed. Now once you put these values, there are two unknowns c1 and c2, there are two boundary conditions which give rise to two equations. So two unknowns, two equations, you get the values of two unknowns c1 and c2. So once you know the value of c1 and c2, you get an expression of u for this situation. Now once you have an expression of u for this situation, next you need to determine q. So what is q? Q is integration u dA. Okay, this will be the area integral, but if the width is fixed, now here we have taken it as 1 meter, it is the integration over the length, that is the length over which we are integrating, u v dy, or sorry, u w dy Now the value of w is 1 we have considered. So integration 0 to b u dy. After that you find an expression for q. Now for the given problem, the value of q equal to 0 means you need to determine what is the value of dp by dx for which q equal to 0. So if you substitute or if you make q equal to 0, what will you get? You will get dp by dx is minus of 6 u mu by b square, which is coming out to be 94 Newton meter per second per meter. So if this problem is clear, let's move to the next problem. Okay, so it is little bit more complicated in comparison to the previous one. Okay, so there is a rectangular duct. So what is a rectangular duct? Rectangular duct is nothing but, say there is a pipe only, but its cross section is rectangular. Okay, not circular. It's not circular but rectangular. Okay, so water enters a rectangular duct. There is a rectangular duct. Okay, so this is the rectangular duct. Water enters the rectangular duct at a rate of 10 meter cube per second. So at this end, water is entering this rectangular duct at a rate of 10 meter cube per second. Two of the faces of the duct are porous. Okay, so two faces of this duct are porous. On the upper face, water is added at a rate shown by a parabolic curve. Okay, so this is the rate. Means, see, first of all, there is a rectangular duct. At one end of the duct, water is entering at a rate of 10 meter cube per second. Okay. Then there are two faces of the duct which are porous. So if they are porous, what does it mean? Water can leave or enter. Okay. So on the upper face, okay, on the upper face, water is added. Okay. So since this is porous, water is added at a rate. Now it is represented by a distribution, okay, which is a parabolic curve. Here at this end, the end at which water is entering at the rate of 10 meter cube per second. Here the rate at which water is entering is 0, and at the other end it is 3 meter cube per second per unit length. Okay, but the profile is parabolic. While on the front face, okay, so on the top face it is given, on the front face water leaves at a rate linearly. Okay, so this distribution is linear. Okay, distance from the end. And what is this linear? Means, see, at one end it is 0 and at the other end, means the end at which the water is entering, it is 5 meter cube per second. Okay, now what is the average velocity? Now see, this is the situation. At one end water is entering at a constant rate of 10 meter cube per second. Through this porous face, water is entering following a parabolic distribution or following a parabolic profile, where the maximum value at one end is 3 meter cube per second per unit length, and on this front face the water is, okay, and the water is leaving, okay, the water is leaving at a rate of 5 meter cube per at a maximum rate of 5 meter cube per second, okay, at one end, and the variation is linear. Now we have to determine the average velocity, means the velocity v2, average velocity, the velocity with which the water leaves the duct, okay, leave this pipe. Now it is given that the length of the pipe is 1 meter, okay, and the cross sectional area, it is a rectangle and the cross sectional area is 0.1 meter square. Okay, so it is slightly unconventional. So there is a rectangular duct. At one end water is entering, at the other end water is leaking. Two of its faces, it is the top face and the front face, are porous. Through the top face water enters, okay, following a parabolic distribution. Through the front face water leaves or water leaks following a linear distribution. The maximum values of these rates, okay, for parabolic distribution, that is on the top face is 3 meter cube per second per unit length, and for the front face it is 5 meter cube per second per unit length. Okay, and you need to find the value of v2. So the Cartesian coordinate system adopted is x, y and z. Okay, so let us see how we can solve this problem. So first of all, consider the top surface. Okay, first of all, consider the top surface. The water enters the top surface as it is given in the question following a parabolic manner. So let us first of all find this parabolic distribution. Okay, so let's that parabolic distribution is given by w. Okay, why w? This w is nothing but the component of velocity. See, you can see that this is the this is the z direction. So this movement is along z direction, negative z direction. So the z component of velocity is what? The z component of velocity is w. So let us say w is equal to ay square plus by plus c. Okay, why y? Why y? Because this variation is along the length. Okay, and this is which axis? This is y-axis. Now see, you are free to choose a Cartesian coordinate system, okay, a convention of your own choice, but in this particular problem we have taken this as x, this as y, this as z. You can choose anything according to your convenience, but in that case you need to determine these expressions carefully. Okay, so w is what? It is the flow rate per unit length at top face. Okay, now what are the boundary condition at y equal to 0? Okay, at y equal to 0, at y equal to 0, w equal to 0, right? At y equal to, this total length is 1 meter, so at y equal to 1, w equal to 3. Okay, further at y equal to 0, at y equal to 0, okay, what will be the slope of the w at y equal, see here it is, here it is maximum, right? Here it is maximum. Now at y equal to 0, dw by dy, okay, dw by dy means the slope of this w with respect to y, what will be this? 0. Okay, so there are three unknowns, there are three conditions. If you use these conditions, you will be getting w equal to 3y square. Now if you consider the front face, okay, now if you consider the front face, which is a linear variation, so for linear variation, let us say u is equal to my plus d at y equal to 1, okay, at y equal to 1, u equal to 0, at y equal to 0, u equal to 5. Okay, so there are two unknowns, two equations we have got, d equal to 5, m equal to minus 5. Okay, so we have determined the, the profile, okay, the mathematical form of the profiles through which the water is entering through the top face and by which the water is leaving the front face. Now for steady incompressible flow, the continuity equation is, you have to area integral or double integral over the control surface v dot dA. This is equal to 0. So this is nothing but the continuity equation. How this is continuity equation? Continuity equation is del rho del t plus, okay, steady incompressible, sorry, so del rho del t del dot rho v equal to 0. Okay, this is the integral form of the mass conservation equation. If it is steady, this part becomes 0. What you are left with is del dot rho v. If it is incompressible, del dot v equal to 0. So that is one form, that is the divergence. And how you are getting this form? This form you are getting from the Reynolds transport theorem, because this is the differential form, and Reynolds transport theorem if you use, then it is del t of triple integral rho dv plus double integral over the control surface rho v dot dA. Okay, now if it is steady, this part is 0. If it is incompressible, rho will come out, so we are left with only the area integral v dot dA, that is the integral over the control surface, okay, equal to 0. So this we are getting from Reynolds transport theorem. Now if we choose this interior of this duct, okay, this much length, duct of length 10 meter as the control volume, then how you can use this equation v dot dA through this phase, okay, 10 meter cube per second. V dot dA is what? V dot dA is nothing but the discharge, okay, 10 meter cube per second minus of 10 meter cube per second. So minus of, see what is 3y square? 3y square is, so ones that which are entering, we are denoting it by negative. So minus 10 minus of 3y square dy, but 3y square di for how much length? For a length of 1 meter. So integrating 0 to y, then the water that is leaving is positive, so 0 to 1, 5 minus 5y, okay, and then v2, okay, so what is leaving? v2 into, sorry, v2 into 0.1. So in this equation, these are very simple integrals. When you integrate, you can see that the only unknown in this equation is v2, which is 85 meter per second. So I hope this problem is clear. In case of any doubt, you can please ask. Okay, in that case, let's move to the next problem. The analysis of a fully developed laminar flow through a pipe can alternatively derive from control volume approach, that is the Reynolds transport theorem. Derive the expression Vz, okay, r square by 4 mu minus of dp dz 1 minus r square by r square, starting from the control volume approach. Okay, so you need to use the control volume approach. So there is a pipe, okay, there is a pipe whose radius is r, okay. Now the coordinate axis, see, this is the z, okay, this is z, this is the radial direction dr, okay, the radial direction dr, okay. So for this pipe we have to determine what is the, see, this is the z direction, so the expression for Vz, okay, means the variation of V, okay, the variation of V with the z direction is r square by 4 mu minus of dp by dz. So this is the z direction, 1 minus r square by r square, okay. So dp by dz constant, so it basically varies with r, okay. So the fluid, as you must have gone through the lecture, you must know that it moves in a pipe because of the pressure gradient, and this pressure gradient acts in the direction of the axis, that is this z axis, okay. And in the sections perpendicular to it, the pressure may be regarded as a constant, means in this section, so this is the axis, so in this section, in any section perpendicular to this, you consider to this axis, the pressure gradient is constant, is regarded as constant. Now due to viscous friction or due to viscosity, okay, or viscous forces, individual layers, okay, so you can consider that there are individual fluid layers, okay. So this is one fluid layer moving adjacent to another fluid layer. So when these two fluid layers move, what happens? When these two fluid layer moves, there is viscosity, okay, between these two layers, which produces shear stress, okay, and this shear stress is proportional to del Vz by del R. Now in order to establish the equilibrium condition, okay, what we do, Newton's second law of motion or the force, okay, the equilibrium in terms of force, okay. So we consider a fluid cylinder of length delta L, okay. So let us consider a fluid cylinder, a elementary fluid cylinder whose length is delta L. So this is the cylinder, okay, and its radius is r, okay. So radius is r, there is a fluid cylinder whose radius is r, okay. So this is the cylinder whose length is delta L, okay. So this is the cylinder, radius is r, okay, length is delta L. Now see, on this face the pressure is P, this face P plus delta P, means at a distance downstream by delta L, P plus delta P. So what is the net pressure force? P minus P plus delta P. Now what area it is acting? It is acting on pi r square, okay. Now this should be equal to the resistive viscous force or the shear stress, okay. So shear stress is tau multiplied by area, now 2 pi r delta L. Now why 2 pi r delta L? So this is the pipe, okay, or the cylinder. Now the viscous stress is acting over this entire surface. So if you cut this cylinder, okay, if you cut this cylinder, you will be getting a rectangle, okay, rectangle whose length is the length of the cylinder delta L, and the other dimension, what is the other dimension? Other dimension is the circumference, which is 2 pi r. So it is 2 pi r delta L. So from this equation, the value of del Vz by del R is 1 by twice mu delta P delta L R, okay. Sorry, delta P by uh, delta Z R, okay. Now upon integration Vz, okay, you can simply integrate it with respect to R, 1 by 4 mu delta P or dP by dz R square plus some constant. Now how to determine the value of this constant? Now you can see that at R equal to R, okay, at R equal to R, what is the value of Vz? The value of Vz equal to 0 because of no slip condition. Hence the value of K is minus of 1 by 4 mu dP by dz R square, and thus Vz is R square by 4 mu minus of dP by dz 1 minus R square by R square. So that is what we need to prove, okay, that is what was asked in the question. So if you summarize, okay, if you summarize, this is a very simple problem. How this is a very simple problem? Again, see, you can solve this problem from Navier-Stokes equation, but for that you need to use the radial coordinates, the Navier-Stokes equation radial coordinates, or what you can do is you can directly take an elemental cylinder, okay, and there you can apply the Newton's second law of motion or the force equilibrium condition, and you get the differential equation and you apply the appropriate boundary condition. So in case of any doubt, please ask, otherwise we will move to the next problem. If there is no doubt, then let's move to the next problem. So in the laminar flow of a fluid in a circular pipe, the velocity profile is exactly a parabola. Okay, in the question it is given that when there is a laminar flow of a fluid in a circular pipe, the velocity profile is exactly a parabola. The rate of discharge is then represented by volume of a paraboloid. Okay, prove that for this case the ratio of maximum velocity to mean velocity is 2. Okay, so just in this earlier problem we have derived the expression for the instantaneous velocity. Okay, not instantaneous exactly, means the variation of velocity with r. Okay, so using this expression you need to determine the maximum velocity and the mean velocity for a circular pipe, and you need to prove that the ratio of the maximum velocity to mean velocity is 2. Okay, so I'm giving you 5 to 6 minutes for solving this problem, and then we'll discuss the solution. Okay, could anybody solve this problem? Let's discuss the solution. Okay, so you have already seen Vz is equal to r square by 4 mu minus of dp by dz 1 minus r square by r square. So you can see that Vz varies with small r and the variation is parabolic. Okay, so it is given in the question also. It is exactly a parabola and the rate of discharge is then represented by volume of a paraboloid. Okay, so the same case. So see, if you look at this equation, okay, let us write this equation. Vz is equal to r square by 4 mu minus of dp by dz 1 minus r square by r square. Okay, now this is 1 minus r square by r square. Okay, now see, in this particular equation Vz will be maximum. Okay, the value of Vz will be maximum. This is a constant, this is a constant, when the last term, that is 1 minus r square by r square, when this term will be maximum, Vz will be maximum. Now for this term to be maximum, this has to be minimum. Okay, so what is the maximum value? 1 minus something. Okay, so 1 minus something, the maximum possible value is when, what is the maximum possible value? Maximum possible value is when r is equal to 0. When r is equal to 0, this is it, this becomes 0. Okay, and this becomes r square by 4 mu minus of dp by dz. So Vz max is equal to nothing but r square by 4 mu minus of dp by dz. So in the same expression we can replace this first two terms by Vz max. So Vz equal to Vz max 1 minus r by r whole square, or r square by r square. Now what is discharge? Discharge is Vz into dA. Okay, area integral. Now if you consider a thin ring, okay, of thickness dr through which the water or the fluid is coming out, then the circumference 2 pi r, the means the area through which it comes out is 2 pi r dr. Okay, Vz is Vz max 1 minus r by r whole square, and the integration is from 0 to r. Okay, now if you simply, this is a very simple integration, if you simply integrate this, you will be getting q is equal to Vz max pi r square by 2. Okay, now sorry, what is mean velocity? What is mean velocity? Mean velocity, see, q is equal to area into velocity. In this expression, this particular velocity is the mean velocity. So the mean velocity is q by a. We have already obtained the expression for q. Okay, so what is the expression for q? It is v max. Okay, it is Vz max divided by pi r square divided by 2. Okay, now if you look carefully, V max is what? V max is the maximum velocity. Maximum velocity into area is the maximum discharge. So half of maximum discharge. Okay, so Q is equal to Q max by 2. That is again one important conclusion. But okay, we know what is Q. So this divided by area. Area is what? Pi r square. So average velocity is V max by 2. So average velocity is maximum velocity by 2. So the ratio of the maximum velocity to mean velocity or average velocity is how much? This is 2. So for this problem also, what is important is this particular expression. Okay, the expression for Vz. Okay, so that's why I have taken up this problem to highlight this point. It is very important even from competitive exam points of view. Vz, expression for Vz. Vz is equal to r square by 4 mu minus of dp by dz 1 minus r square divided by r square. Okay, and this first part is nothing but the Vz max. I hope this problem is clear. In case of any doubt, then please ask me. Okay, thank you. So let us move to the next problem. The velocity distribution for a fully developed laminar flow in a pipe is given by u is equal to r square by 4 mu del phi by del z 1 minus r by r whole square. That is the expression that we have just seen. Determine the radial distance from the pipe axis at which the velocity equals the average velocity. So if you have understood the previous two problems, then if you have understood the previous two problems, then this is a very simple problem. So please take 5 to 6 minutes and try to solve this problem, and then we'll discuss the solution. Okay. So these expressions we have already seen. This u actually is nothing but the vz. Okay. So you have to determine the radial distance, means the value of r for which the velocity at which the velocity equals the average velocity. Okay. So please try this problem and let's see. Okay, okay, fine. 0.71 R. Let's see. Okay, let's see. Okay. So for a fully developed laminar flow in a pipe, we know that U is equal to U minus of R square by 4 mu del P by del Z minus of R minus R whole square. Okay. Now we have also seen that a V average is Q by A, that is discharge by area. So 1 by pi r square 0 to r minus of r square by 4 mu 1 minus r by r. So this we have just done. Okay, so average velocity we know. Now when u is equal to v average, okay, when u is equal to v average, so simply in place of u need to replace it by v average, and then find that the value of r by r square equal to half, or r is equal to 0.71 r approximately. Okay, so yes, the answer is correct. So I hope you are able to do it correctly, Praveen. So you have understood the concept. Okay, very good. So this particular lecture, uh, uh, this particular live session, which is related to the Navier-Stokes equation, is very important. You will find ample problems. Okay, you will find ample problems in the standard books. Okay, so you need to practice some more problems in order to determine this. Now, I don't know. Praveen, please answer when we are discussing this particular problem. Were you there or you joined later? Later, fine. So I'll just discuss this problem once more. Okay, so that you can understand. So what is this problem? There is a rectangular duct. Okay, so rectangular duct is nothing but it's like a pipe. Okay, so there is a rectangular pipe. There is a rectangular pipe. Okay, now through this end of the pipe, okay, through this end of the pipe, water is entering at a rate of 10 meter cube per second. Okay, and through the other end, the exit velocity of the water is v2, which is the unknown and which you need to determine. Okay, the top face of this rectangular duct or pipe is porous, and the front face is also porous, as shown in this figure. Okay, so the top face is porous and the front face is porous. Through top phase, since it is porous, sorry, water is entering following a parabolic distribution such that here it is 0 and here it is 3 meter cube per second per unit length. Okay, similarly, the distribution following which the water leaves the front surface, which is also porous, it's linear. Okay, and here it, it is 5 meter cube per second per unit length, that is the maximum value, and here it is 0. Okay, so now you need to find what is the value of V2. Okay, so since not much time is there, I will not ask you to solve it, but rather I will just discuss the solution. Okay, so for this top face, it is, see, here the maximum values for this parabolic distribution at which the water is entering, and for this linear distribution for which the water following which the water is leaving the front face, okay, is given. But the distributions, okay, the exact mathematical form of the distributions are not given, so that is our first task. Okay, so let, for this one, the top face, w is equal to ay square plus by plus c. Okay, where a, b and c are constant. You see, this is, sorry, this is the coordinate axis y, z and x. Okay, okay, one more thing which I forgot to tell you. The length of this pipe is 1 meter and the area of this cross section is 0.1 meter square. Okay, now say the parabolic distribution is ay square plus by plus c. Okay, Now in order to determine A, B and C, you need three equations. So the first equation is at y equal to 0, what is the, see this distribution is W. So at y equal to 0, what is the value of W? It is 0. At y equal to 10, what is the value of W? It is 3. Okay. So at y equal to 0, W 0, at y, sorry, not 10, at y equal to 1. It is a length of 1 meter, W equal to 3. And here at y equal to 0, what is the gradient with respect to z? That is also 0. So three equations, three unknown, you can solve it to get the value of A, B and C. So C and B came out to be 0, A equal to 3, so W equal to 3y square. Similarly, for the front face it is linear profile. So for this linear profile, it is, say U is equal to, say the rate at which it is coming is U is my plus d. You need to determine the value of m and d. At y equal to 0, the value of U is 5. At y equal to 1, it is 0. Okay, so using this two unknowns, two equations, the value of m and d are minus 5 and 5, and u is equal to 5 minus 5y. Okay, now from Reynolds transport theorem, RTT, for steady incompressible flow, what is the continuity equation? It is v dot dA equal to 0. So following this one, what you can write? See, all the inflows to be negative, considering all the inflows to be negative and all the outflows to be positive. Okay, so here at this phase the inflow is minus 10. At this phase the inflow, see, the variation is given 3y square, okay, into dy, but from where to where? From 0 to, from 0 to 1. So integration from 0 to 1, because these two are inflows, that's why negative sign, and the other one is the outflow, that is through the front phase, that is linear variation 5 minus 5y dy 0 to 1, and v2 is also outflow, so v2, and the cross sectional area is given 0.1. So in this equation these are very simple integration. Once you integrate this, you'll be getting the value of v2 as 85 meter per second. So see, this is also a very simple problem, but it's little bit unconventional. So you refer to any standard book, you'll find plenty of problems. Okay, you need to solve some problems that will give you a much better idea. I hope this problem is clear. Okay, fine. So let's stop here, and happy Dashera to everyone. Thank you. You can please leave the meeting.